Okay, so like I said, one of the important things we want to remember is what have we visited during our traversal? Okay, the simplest way to implement this is to think, well, I know I can create a Boolean array, and we can just call this visited, sake of arguments, and this is just a new Boolean array. Okay, in our graph, we have 1, 2, 3, 4, 5, 6, 7 nodes. So we can create that in advance. And then what we kind of visualize is that we have this array, 1, 2, 3, 4, 5, 6. Okay, there are 7 elements. We start from 0. And by default, a Boolean array will mark all these as false, all these positions in the array. Okay. We take advantage of that. So basically false in this array means we haven't seen anything yet. Okay. The other thing we might want to have is a queue. Okay. And again, a queue can be something as simple, he says simple without really meaning it, as a linked list of integer type. And this can be just called queue. Regret not just calling it LL, but let's actually do proper Java. Okay, I forgot my semicolon there. And if you look in the linked list documentation, there are methods for add first or add last and get first. So you can use a linked list as a queue. And again, all we're going to have, just we imagine this just as we have a queue that's going to eventually get filled up. Just it starts off empty. Other thing we think about is the recursive call stack. Okay, and basically we're going to call whatever our particular algorithm is. Maybe it's a depth first search starting at 0. And we're going to call this method, and this method will get called recursively. So as we traverse this graph, we will form a call stack. Okay, so this particular traversal isn't really anything important, but we'll start at 0. Okay, so I'm starting here. Let's say I'm going to do like a depth first search. Okay, so I would pop 0 onto the stack. Okay, immediately once I've visited this, maybe I perform the visit action. I print out whatever it's going to be. Doesn't matter too much. Then I can mark that I have seen this particular node. Okay, I can also, if I want, I can put that onto a queue. Okay, so the first thing we have is we're at vertex 0. Okay, we can look at the neighbors of 0 and find, well, we have 2 and 1 are adjacent, so those are neighbors. We might want to in-queue those, that we want to go to there eventually. And we can also mark, okay, we have seen them, okay? So then we can make a decision. Let's say I'm following the queue. Okay, well, I would remove the first one and then move to 1. Okay, so now my call stack, I have opened this first recursive call. Now I have a second recursive call. Okay, now I have seen 1. We can mark that as true. Okay, and then we think about the neighbors. Well, I've already seen this. Okay, so there'll be no point adding that onto a queue, but I can see 3 and 5. These haven't been visited yet, so maybe they can go onto my queue to visit later on as well. Okay, then let's just take this off the queue. And because we're letting the queue guide our traversal in this case, then we will, do I want to do it that way? Yeah, I'm going to ignore the queue for now. I'm just going to add the data, but let's just, for sake of argument, say I'm here, I can see 3 and 5. So let's go to 5. Okay, so my call stack then forms this kind of memory like this. At 5, we've seen something new, we can add it on there. We're at 5, so we've now visited 5. Okay. I can go to 3 or 6, but I've already seen 1. We know we visited that. Or, yeah, so I can, maybe let's go this way. Again, the direction won't actually matter. Okay, so I'm now at 3. The only new information I can see there is 4, so I'm going to add that to my queue. I'm not really using the queue here. Okay, I can see we've now visited 3. So we have 0, 1, 5, 3 in our stack. Okay. We haven't visited 2, still false, or 4. So if I'm sitting here, we have visited 5, so I don't need to go there. So I can, let's say, go to 2. Okay, so now my call stack 3, 2 is like this. Okay, and at this point in time, well, all I can see is 0 and 3 when I'm sitting at 2. Okay, so I need to be able to get back to where I still have options. Okay, so I have options here and here. Okay, so if I am at 2, I've already visited 0, there's nothing else to do, then I can, this method will end, there's nothing else it can do, and then it will pop off. So then we come back to 3, 5, 1, 0. Okay, so we're now at 3, and we can see 4 from 3. So then we can say, well, let's go there. Okay, mark that as true. Okay, so then 0, 1, 5, 3, 4. Once we're at 4, the only thing we have, oh, sorry, I forgot to mark that off as true. Once we're at 4, the only thing we can see is 3 and 6. We've already visited 3, so that's true. The thing place we need to go next is 6. Okay, so 0, 1, 5, 3, 4, 6. Okay, we go here, and then we mark that as true. Okay, at this point in time, at 6, we can only see 4 or we can only see 5. We've already visited something here, so we check, have we visited that? If we have, then at this point in time, we're pretty much done, and our algorithm, all those calls will just start to collapse. So 4, 3, 5, 0, 4 will pop off, 3, 5, 1, 0. And again, the algorithm just kind of retreats back. 5, 1, 0, 1, 0, and just 0. Okay, so this is a kind of stacking up of calls as we navigate through the graph. Now remember, each time we start a recursive call, the method doesn't end immediately. Okay, so we're still waiting for these to end. So once we get to the very end and we can't go any further, we kind of reach a base condition, and then the whole structure just collapses back again. The really important thing here to notice is we have a data structure for what we've already seen, a plan for where we should go next if we need it. We didn't really use it in this case. And then also a kind of route back from where we have been, okay, tracing this journey. Those are the 3 types of memory that are very useful to have when we're trying to do a traversal.